Okay. Um, so we are going to start with a little reminder of what we did last time, if you were here. We were talking about electrochemistry, and I said we were talking about electrolysis. Electrolysis is where a current is applied to a solution or a molten substance and splits the chemicals inside it. It has two parts to the word: electro, something to do with electricity, and lysis, meaning breaking. And what we're going to do today is we're going to continue that um, journey. So here we are. I hope in a moment you will see this. Okay. So this is electrolysis 2. If you missed electrolysis 1, it is recorded and it is somewhere on the net. I can tell you where if you need it. Here we go. So this lesson is in two parts. The first one is trying to work out what products are made in any electrolysis, and there are some rules to go with this. And the second one is using something called Faraday's first law, which allows us to calculate how much of a chemical will be produced if we know the current and the time. But firstly, we're going to look at the first one, which is about predicting what is going to be produced. Now, there are two types of electrolyte. Electrolyte is a liquid which conducts electricity and is broken by it. So mercury is not an electrolyte. It is a liquid, it does conduct electricity, but it is not broken by it. But molten salt, sodium chloride, it conducts electricity, it is a liquid, but it is broken into sodium and chlorine. Now, when we are trying to work out what is formed, if they are molten, it is really easy to work out what is going to be made. And most industry uses molten solids. It's a bit more difficult with aqueous solutions when we have water there because it's got the water there, but we'll look at it. It's not too much more difficult. So if we have a molten electrolyte like salt, salt melts at 801 degrees Celsius, and when it has melted, it separates completely into ions. And this is something that I want you to understand very clearly from the very beginning. That if we have sodium chloride and it is liquid, that means molten, then it will actually exist as completely separate sodium and chloride ions. If I have sodium chloride and it is AQ, it also forms Na plus and Cl minus ions. But there is also in this the possibility of it producing H plus AQ and OH minus AQ from the water. Okay, now that's very important that you understand that the ions are completely separated and they do not have anything to do with each other at all. That is really, really important. Okay, so there are only Na plus and Cl minus ions, so there are only two products, sodium and chlorine. Now, last time we wrote some ion electron or discharge equations. Here are some. So the Na plus are cations. If you remember, we said that cations, if we spell it Ca plus instead of T, then we remember that cations are positive and they're attracted to the cathode. We drew two cats last time staying together. So that means the cathode must be negative. When they arrive, the Na plus, pick up electrons and become atoms of Na, like that. Really simple. Na plus one electron goes to Na. Cl minus are anions. If you remember from last time, I said that's a negative ion. Okay, negative ions are called anions. So they're attracted to the anode, which must be plus. And when they get there, they lose electrons like this. Because they are Cl2, we have to write 2Cl minus 2 electrons equals Cl2, or, and this is important, we said this last time, you could write 2Cl minus is Cl2 and 2 electrons. Doesn't matter whether we write that or this, they're both correct. Okay? I hope that's okay so far. Okay, so here's a little bit of practice for you again. This time, what I'd like you to do is just to try to write the discharge equations for these. Some of them are positive, some of them are negative. Just try and write the equations for them, okay? Just have a go and see if you can write the equations for them now. Cu2 plus, Al3 plus, K plus, Cl minus, and O2 minus. Just everybody have a go, write it down on a piece of paper, and then if you get it right, well, if you think you've got it right, just show it me. So there they are. Have a go. Just like the Na plus, just like the Cl minus, same idea. See if you can write the equations. I think you can. St. Michael's, the idea was to have a go at the equations to see if you can do the equations. Mathari, well done. Kabiro, well done. St. Michael's, are you going to have a go? I'll do the first one to make sure everybody knows what they're doing. So if I have Cu with a 2 plus, then I need to add 2 electrons to it, and that will make Cu. Simple. What we need is to make the atoms. Okay, this is an atom. This is the ion. The Cl minus will have to lose electrons, so you need to work out what is happening. So everybody have a go. Anybody done it? Anybody want to show me the answer? Come in, Kabira, let's have a look. Yes. Yes. Correct, Mathari, correct. Kabiro, down at the bottom, Cl minus. No, Kabiro, down at the bottom, we can only gain or lose electrons. And if we are negative, we need to lose electrons. So let's just look, because Mathari and Kabira have done this, and St. Michael don't look as though they're trying to. So let us have a look. So with aluminium, because it has 3 plus, we have to add 3 electrons. Each electron has a negative charge, okay? So if I add 1, that takes off 1 plus, okay? So 3 of them are needed to get rid of that. K plus, only 1 electron will make it K. Now the Cl minus, it has to lose electrons. So the Cl minus, either I write minus, whoops, either minus an electron goes to Cl, and then I think, okay, I need Cl2 because it always exists as Cl2. So then I would need 2 Cl minus and minus 2 electrons. Or I can write 2 Cl minus turns into Cl2 and 2 electrons. The oxygen, again, oxygen goes around as O2. So we'll have to lose electrons to become O, but it's O2, so 2 O2 minus, and therefore 4 electrons, or 2 O2 minus turns into O2 and 4 electrons. Okay, so those are the sort of equations we're going to be writing. Okay, that's quite simple. I hope that makes sense. I hope they all make sense to you now. So let's move on. So let's have a look at molten lead 2 bromide when it's being electrolyzed. Molten lead 2 bromide is PbBr2. Okay, PbBr2. Now, because it's molten, that's the only 2 chemicals that can be produced. Let me just change the color. Hang on. Okay. So PbBr2 can only produce lead and bromine, and it goes around as 2 atoms joined together. Okay, so that's what's going to happen. Let's see what it looks like in a proper experiment. So this is a crucible. I don't know if you've ever seen one of these, but it's spelt, oops, it's spelt C, oh, hang on, stop just a minute. It's spelt Crucible, crucible. Whoops, I've drawn 2 E's on the end of that. I do not know why. Crucible, that's what it's called. Okay, the little thing we can see there. Okay, here we go. Bromide is a solid at room temperature. So this is the experiment. This is lead bromide. It's a white solid and it needs heating to melt it. We have 2 electrodes going into it, and the 2 electrodes pass electricity through it. When the electrolysis starts, you see this brown gas. I don't know if you can see, but there's a brown gas and some bubbles with some brown gas coming off, okay? So it's producing a brown gas, and it is also producing something else. If we pour this out at the end, you will see that there is something else there. So these electrodes are made of carbon because it's inert. Here it is afterwards when they have poured it out, and there in the bottom is lead. Okay, so that's lead stuck in the bottom of it. So in other words, my lead, oh, sorry, why is this not writing? Oh, I'll do it in just a minute. So the crucible contained, produced back here, Here's the brown gas coming off, that's bromine. And here is the solid lead there, lead bromide left at the bottom. And the lead was melted by the heat. So we don't see very much. I mean, it's just silvery metal at the bottom. Okay, so let's just have a look at what's actually happening. So I'm going to just stop showing that, and I'm going to show you something else. So here we go. So I'm going to deal with what actually happens in the electrolysis. So I'm going to say at the cathode first, and then I'll do the anode, okay, at the cathode and the anode. So what we've got is two carbon rods going into the crucible, and in here we have the PB BR2 liquid, okay? And we have a battery here like this, okay? Now the long line is always, I'll make that a little bit bigger for you, I hope. Can I make that a little bit bigger? Yeah, that's a bit better. So the long line here is the positive, and the short line is the negative. Now, the negative one means that this electrode here will be, because negative will attract the positive ions, and we said cations are, if I write it like this, it helps me remember that they are positive ions. And cations go to the cathode. So that means that the cathode is negative and the cations are positive. Okay? Please do not write on my whiteboard. Thank you. The anions, therefore, are negative, and they go to the anode, which must be positive. So this is the anode over here. Whoops. Here. And this is the cathode over here. Okay? So let's move up a little bit and work out what's actually happening in here. So if I look at the cathode, just at the cathode to start with, okay? So I'm going to draw the cathode, and this is made larger, and it's made of carbon, and it's attached to the minus. Now, because it's attached to the negative, it is full of electrons, okay? It is full of electrons. And because it is negative, the lead ions are attracted towards it, okay? When they get to it, the lead ions steal the electrons, so 1 and 2. And that's the lead 2 plus picking up 2 electrons and turning into lead. So the lead then falls to the bottom because it's very heavy. So as those two go, so let's just get rid of those two. What is happening? Get rid of that one there. And that one, okay, they've gone. And the lead has lost its charge, so now it can fall down to the bottom. Now what happens is that the battery pushes some more electrons in here, so some more electrons come in. Mathari Mix, do not use this board. Thank you. The lead 2 plus here, another lead comes along, takes 2 more electrons, loses its charge. Okay, so it loses its charge. So those 2 electrons, those 2 go. This loses its charge. And now this lead as well drops to the bottom. Okay, so that keeps on happening so that the electrode keeps on filling up with electrons. Guys, just leave your cursors off the picture, please. Thank you. Okay, the electrons fill up all the time. Now that means that if I have up here, if I have my battery up here, let's get rid of that. Here's my battery. Short line is the negative. Here's the positive one. That the electrons must be coming from somewhere else. Well, the other electrode here is positive. Now, if it's positive, there's something really rather important you have to remember, and that's this. Electrons can't swim. Now, that's a stupid thing to remember, but electrons can't swim means that electrons cannot be in the molten substance. Okay, just can't be there. So that means if I take, let's say I take this wire off, and let's put a bulb in here. If this is connected and working, then this will light up. So light will be coming out of the bulb. Now, if that is happening, that means electrons must be moving here, and that means they must be moving here as well. So to do that, we need something happening on this electrode. And what is happening is this. I have Br minus, which are attracted towards the electrode. When they get there, they lose their electrons to the electrode. If they do that, then they're not charged anymore. But those electrons are now on here. Here they are. And these two BRs join together to become bromine. And the bromine comes out the top as a brown gas. These electrons then get pumped round by the battery to this side where they're being picked up. So let's look at that again. Br minus and Br minus lose their electrons onto here. Because they've done that, they are now not charged. The electrons are now on here and will be moved towards the plus. This is the positive end here. So they will be attracted towards it and pumped round. A battery is basically just a pump of electrons, okay? A cell or battery is just a pump of electrons. So we can describe it as an electron pump. Please, Mathari, put down your cursor. Thank you. So the bromines disappear outwards and the lead drops off the bottom. Mathari, please don't. Thank you. Okay, so that's what's happening. So let's go back. Here we are, anode positive, cathode negative. In here, the ions. Lead bromide, completely separate. If the anode is positive and the cathode is negative, the cathode is full of electrons. Mathari mixed. Please do not do that. It is disrupting other people's watching. So the cathode is pumped full of electrons. The lead ions come up to it and take the electrons away. And over here at the other side, the BRs do a similar thing, only they are producing. So they are producing the electrons. So Br minus turns into Br2 and electrons. And those electrons go into here and up and round. Okay, so the whole thing works. Okay. So that is what is actually happening inside the electrolyte. The electrolyte just being a liquid which conducts electricity and is broken by it. Hello, Dandora girls. How nice to see you. So let's go back to the presentation. Here we go. So in this film, we saw lead being formed, we saw bromine being formed, and that is how it works. Okay, so that means that the electrolysis of molten things is really simple. Whatever it is, there are only two ions and therefore only two products. But the electrolysis of water allows something else to be involved. So if we've got AQ, then something else is formed. Something you have to remember is that water, pure water, does not conduct electricity, at least not at very low voltages. If we want it to conduct electricity, we have to help it conduct electricity, and that normally means adding a small amount of sulfuric acid. The sulfuric acid doesn't change. In other words, there is the same amount later, but it helps the water to conduct. So what happens? Well, here is a little experiment. Oh, Deliveroo, that's nice. I'm glad. Oh, we can get a pizza. Ah, good. I'll send you a pizza. So here is a speeded up version of the gases being produced. And we'll see it again in just a minute. But here it is. Watch this. This is speeded up. But as you can see, oops, sorry, just too far. As you can see, one of the tubes has much more gas in it. The gas has gone all the way down to there, whereas in the other one, the gas has only gone down to about there. It's difficult to see, but there it is. So this is the electrolysis of water. One of them is producing like 8 cubic centimeters and one of them just over 4. Okay, so let's see what happens. So this is an experiment in which they have two metal rods in the bottom of a beaker, a square beaker. They fill up the tubes with water and then they put them over the electrodes. The wires are then connected to a battery. This is something that is quite easy to do. The battery sends electricity through, and immediately we see bubbles of gas being produced. Now, those bubbles of gas, it looks like there is more in the right-hand one. The right-hand one is the black one, which is the negative one. Okay, that is negative. Now, if they speed up the video a little bit, you will see what happens. It's difficult to see to start with because there is only a small amount, but here it is speeded up. Watch it going down and watch this one going down, and you'll see the one on the right is about twice the volume, right? I'll just stop it just for a minute. There, that's at 8, and this is about 4, okay? Probably just past 8 and just past 4. So it is twice the volume. They're at 10 and just over 5. Now we can test the gases. We can test the gases by just taking the tube out and trying to set light to it. That's the best way of testing this gas here, because the one on the right is likely to be hydrogen. We'll see why in just a minute. So there, I'm going to pick up this and watch a little light. And did you see that? That is a small explosion. Watch it again. Watch as it goes in. There, a little explosion. That is a flammable gas. That is hydrogen. If you could hear it, you would hear a pop. Now, the other gas, they can keep it going for a little while to fill it up and get a bit more. The other one we're going to test in a different way. And the way we're going to test it is to get a lit splint and then blow it out so it is only glowing. And you will see, although this is not very easy to see, you will see that it will have a particular effect. Right, it has been going for a while now. Now there is 10, lots more from this one. So they're going to take it out. There's a splint coming in from the top right. It is only glowing there, just glowing, and there, it relights. Okay, so the glowing splint relights. They can do it again. There it is. You see it glows much more brightly in that gas. So that means we've got hydrogen and oxygen. Okay, so the electrolysis of water produces hydrogen and oxygen. Now that's really important to know, because that means we can predict some of the things that might be formed. So the electrolysis of water, water is splitting. Oops, where's that gone? Water is splitting, and it splits in small amounts into H plus and OH minus. The H plus picks up an electron and turns into H, but it is H2, so we need 2H and 2 electrons. The OH minus is more complicated. It forms water and oxygen and some electrons. Because there are 3 oxygens here, we need at least 3 here, but actually it's 4, and that produces 2 hydrogens, 1 oxygen, and 4 electrons. Now this is important. 2 electrons, 4 electrons. So for each oxygen, we need 4 electrons. For each hydrogen, we only need 2. So if we had 4 electrons, that would make 1 oxygen, but it would make 2 hydrogens. That's why it's H2O. 2 hydrogens to every oxygen. So in aqueous solutions, we get different products which are possible. So let us say we are looking first at, we know that NaCl, if it's liquid, can only produce Na and chlorine. But if it's NaClAq, then it could produce sodium or hydrogen and chlorine or oxygen. So we need a rule, and here are the rules. If the cation is less reactive than hydrogen, it will produce the metal, but otherwise we'll get hydrogen. If the metal is less reactive than hydrogen, then we will get the metal, otherwise we will get hydrogen. Okay, at the cathode, we get either metal or hydrogen. If the metal is more reactive than hydrogen, we will get hydrogen. If it's less reactive, and that is only copper, silver, gold, titanium, platinum, that's all, then we'll get the metal. For the anion, if it is a chloride, sodium chloride, copper chloride, lead chloride, doesn't matter, whichever one it is, then it will produce chlorine. But if it is not chloride, like if it's sulfate or nitrate or oxide or whatever, we will get oxygen. So they are rules worth remembering. At the cathode, we'll get metal or hydrogen. At the anode, we'll get chlorine or oxygen. If the metal is more reactive than hydrogen, it is not produced. It is easier to produce hydrogen. If it's got chloride, then we will get chlorine. Otherwise, we will get oxygen. Okay, so let's try that. So here's some examples. You see if you can predict. Talk to your neighbor, see if you're okay. So this one is sodium chloride liquid. At the cathode, what will we get? at the anode, what will we get? Hopefully, you will think it's liquid. I can only get sodium and chlorine. That is correct. But what about with sodium chloride in water? Sodium chloride in water, it could be Na or hydrogen here, and chlorine or oxygen here. Well, the first rule said that if the metal was more reactive than hydrogen, we get hydrogen. And the second rule says if it's a chloride, we get chlorine. So that means we're going to get hydrogen and chlorine because sodium is much, much more reactive than hydrogen. What about copper sulfate, AQ? Have a think for a minute. What do you think will be produced with copper sulfate in water? Copper sulfate in water. Copper is less reactive than hydrogen. What two chemicals will be produced? Anybody? What do you think will be produced? Dandora girls, what do you think? Oh, no, no, don't talk to us. Kabiro, what do you think? Mathari, what do you think? Copper sulfate in water, what do you think will be produced? Will it be copper or hydrogen? Will it be chlorine or oxygen? St. Michael's, what do you think? Kabiro, what do you think? Anybody want to have a go? No? Just two chemicals. What could be going wrong? Hydrogen or copper? Chlorine or oxygen? Somebody be courageous. Somebody be brave.
Excuse me, sir.
Yes, Dandora?
From Dandora Girls, we think the answer is hydrogen and sulfur.
You're right with one of those. Okay, let's look at it. Let's look at it. The answer is copper and oxygen. Now, the reason it is oxygen is because in copper sulfate, there is no chloride, and the only other thing which can be produced is oxygen. And so at the anode, the only two things that can be produced are oxygen or chlorine. Oxygen or chlorine. Nothing else can be produced. At the cathode, it can only be the metal or hydrogen. That's it. So it can be copper and oxygen. In this one, sulfuric acid. This one's easier because the hydrogen is the same in both. And then we have sulfate, and we've just seen that sulfate is not produced, so it is hydrogen and oxygen. Here are some I'd like you to think about. What do you think is produced in magnesium sulfate? Well, magnesium is much higher in the reactivity series than hydrogen. So at the cathode, what will be produced? What do you think will be produced? Well, it's either magnesium or hydrogen. Because hydrogen is less reactive, it will be, whoops, hydrogen. At the anode, there is no chloride, so it's oxygen. In zinc chloride, AQ, okay, AQ, so it's zinc or hydrogen, which is more reactive. Zinc is more reactive, so we get hydrogen. At the anode, we have chloride or the chlorine or oxygen. When there is chlorine, we get chlorine. Lead bromide. Now, lead is only just more reactive than hydrogen, but this is liquid. So this is Pb and Br2. There is no choice here. With lead bromide in water, well, lead is more reactive than hydrogen, so we get hydrogen, and there is no chloride, so we get oxygen. Okay? Hopefully that will make some sense. Hopefully some sense. Okay. Boom. So this is lesson part 2. Lesson part 2 is about Faraday's law. Faraday's law is all about something really obvious. The first thing is that if you run more electricity through something, it has greater effect. So if I use more electricity, particularly for longer, I get more product. That's obvious. The second thing is that we know the value from Mr. Faraday himself. We know what a mole of electrons is. And a mole of electrons is 96,500 coulombs. A coulomb is an amp times 1 second. Now, 96,500 coulombs is called a mole of electrons or a Faraday or just 1F. Okay? A mole of electrons. Now we're going to go back to this. I want you to look at this, and we're just going to look and try and see something which is very important. Okay. What we're looking at is how much electricity is needed to produce one of each of these. So to produce 1 mole of copper, I need 2 moles of electrons. Okay, so 2 is required there. That will be 2 Faradays. In aluminium, to produce 1 mole of aluminium, I need 3 electrons, 3 moles of electrons. That's 3 Faradays. Faraday being mole of electrons. For 1 mole of potassium, how many electrons? Oh, only 1. Okay. So I only need 1 to produce 1 mole of potassium. How about chlorine? Well, for each mole of chlorine, there are 2 electrons. So that's 2 Faradays. For each oxygen, it's way more. It's 4 electrons. That's 4 Faradays. Now, I don't know if you can see that on my right-hand side. I'll just change the color so you can see it better. So that is saying in the top, we need 2 Faradays for 1 mole of Cu. We need 3 Faradays for 1 mole of Al. We need 1 Faraday for 1 mole of potassium. We need 2 Faradays for 1 chlorine, and we need 4 Faradays for 1 oxygen. Now, these are important. We always have to be able to do this. That's really important. We just look, let's take the aluminium one again. Al, if that is 1 mole there, then how many moles have I got here? Oh, I've got 3 moles here. 3 moles is, whoops, sorry. 3 moles is 3 Faradays. Okay, that's important. Okay, let's go on. Much further on. Okay, how many Faradays are needed to produce? Here we are. This is for you to do. I'm going to do the very first one, and then you can do the rest, okay? So in each case, what I have to do is I have to think, okay, I'm going to write the equation. Then I'm going to look at the question. The question says 1 mole of Na. Well, to produce 1 mole of Na, I need, oh yes, 1 mole of electrons. 1 mole of electrons equals 1 Faraday. Okay, that's 1 mole of electrons is 1 Faraday, which is 1 F. Okay, so you look at all the other ones and try to work out what is formed, how much we need, and then just let's share the answers out of it. Okay, so everybody have a go. How many electrons, how many moles of electrons are we going to need to produce what it says in the question? Two moles of Na. How much would it need? Correct, Mathari. That's for number 2. Can you do the rest? Wamuini, have you got answers? Dandora, have you got answers? Down a bit, please. Down a bit. Well, they're good pictures. They're good pictures, but can you do this, what we have done already just now? That's good, but let's see if you can do this. It's good, Wamuini. It's good. It's good pictures. Dandora, have you done them? I'll do another one because Mathari have got this. So I'll do another one. So if it's 2 moles of Na, well, because Na still is Na plus an electron goes to Na. If I want 2 moles of this, well, 1 mole needs 1 mole of electrons. So 2 moles would need 2 moles. Well, 2 moles is 2F. That's the answer to this one. So we've done that one, we've done that one. Magnesium is Mg2 plus, Al is Al3 plus, and you know about Cl, it's minus, okay? So that's how the second one is done. Can you do the third, fourth, and fifth? See if you can. Mathari, have you got an answer? Uh, 2 moles of Al. 2 moles of Al won't be 3F. 1 mole of Al will be 3F, but 2 moles of Al. Okay, because we want to move on, I'm going to do these for you, okay? I'm going to show you. Oh, have we got an answer there? 2 moles is not 3F, no. Do you want to show me, Dandora? Closer? Closer, please. Bring it closer. That's better. Well done. Well done. So let's have a look at them. Very good. Very, very good. Okay, so 1 mole of Mg is easy because Mg2 plus must add 2 electrons to make Mg. So all we're looking for is I want 1 mole of this. How many moles of electrons is that? Oh, that must be 2 because it says 2 moles. Okay. So 2 moles of electrons give 1 mole of Mg. So what about 2 moles of Al? Well, 2 moles of Al must go like this. If Al is 3 plus, then it must need 3 electrons to produce Al. But what happens if I wanted 2 Al? Well, then I would have started with 2 Al3 plus, and I would have needed 6. That's 6 Faradays. 6 Faradays for 2 moles of Al. And the chlorine, well, the chlorine has to lose electrons, but it works exactly the same. So the chlorine Cl starts as Cl minus, turns into Cl, but it goes around as a pair. 2 of those, 2 electrons. So 1 mole of chlorine, because it goes around in a pair, is 2 moles of electrons. So 1 mole of chlorine is 2 moles of electrons, which is what we call 2F, 2 Faradays. Okay, so how do we find coulombs? Well, coulombs is amps times seconds. Okay, that's really important. Coulombs is amps times seconds. So let's try an example. What mass of Na will be produced if we have 20 amps for 20 minutes? So the first thing we have to do is we have to go, okay, we work out how many coulombs we have. The question will always tell you 1 Faraday is 96,500 coulombs. You don't have to remember this. It will tell you in the question. Okay, very important. You will know this. You don't have to remember it. Okay. So if we work out the coulombs first, we know that 1 mole is that. So here we go. What mass of Na if we start with 20 amps and 20 minutes? Well, firstly, how many coulombs? Well, coulombs is amps times seconds. So that will be, oh, these were examples. We're not going to do this just now. Okay, so here we are. The coulombs is amps times seconds. We have 20 amps times 20 minutes times 60 seconds, because we want to make sure we've got it in seconds, because it's amps times seconds, not times minutes. Okay, very, very important that. Okay. All right. Second, then we think, so we've got 24,000 coulombs. Then we go, okay, here is the discharge equation. So each mole of Na uses 1 electron. Okay, each mole of Na needs 1 electron. Okay, so 1 mole of Na needs 1 Faraday. Now they will always tell you the RAM 23. So 1 mole of Na is 23 grams. Okay, and because it's one of these with one of those makes one of those, to make 23 grams of this, we need 96,500 coulombs. Okay. So we say, okay, how many Faradays have we got? Well, 24,000 isn't a Faraday because a Faraday is nearly 100,000. So we divide the number of coulombs we've got by the number of coulombs in 1, and we get 0.25, about a quarter, 0.2487 Faradays. So if 1 Na needs 1 Faraday, then if we have 0.2487 Faradays, we'll get 0.2487 Faradays, moles of sodium, which will weigh that times 23, 5.72. Let's just look at it again. We work out the coulombs. Coulombs is the amps, 20, times 20 minutes, times 60 to 24,000 coulombs. Then because Na is 1 to 1, that means that from this, I hope you're getting this idea, 1 mole of electrons gives 1 mole of Na. Now, 1 mole of electrons is 96,500 coulombs. Have we got that? No. So what we do is we say, okay, I know. I will see how many 96,500s I have. So I divide the 24,000 by 96,500. That gives me 0.2487. Well, if I have 0.2487 moles of this, look at the equation, 0.2487 0.2487 will give 0.2487. But not grams, that's moles. So the last step is to say, okay, the sodium must be 0.2487 times 23, which is the RAM, and that's the answer. Let's have a look at another one. What mass of zinc if we have electrolysis for 50 minutes and it's 3 amps? See if you want, have a go at that. I will do it in just a minute because we're getting close to the end of the lesson. So 3 amps, turn this into seconds. That will give us the number of coulombs. Then how many Faradays is that? And I'll tell you that the RAM of zinc is 65. So RAM of zinc is 65. Okay, that's another piece of information that you need. And because it's zinc 2, that's Zn2 plus 2 electrons makes zinc. So those 2 pieces of information are really important. Everybody have a go. Anybody want to have a go? Have a go here. Come on, Wamarini, you can do it. Yes, you can. Come on, Dandora girls. Is that the mass that we've got? Wow. Okay, that's pretty quick. Let's see if you're right, huh? Let's wait for a minute and see if you're right. We have a very fast answer from Dandora girls. Show me your answer again with your name there, please, Dandora. Oh, Dandora's disappeared. Oh, no. Dandora, you've disappeared. Where have you gone? Dandora, I can't see you. I don't know if you can see me. I hope so. Yes, Mathari. What's your name, Mathari? Dandora, show me your answer and your name, please. Well done, Gregory. Really good. Show me again, Dandora. I can't see your answer. Oh, you've disappeared again, Dandora. You're closer. You've got twice. You have forgotten that zinc needs 2 electrons, so you will get half as much. No, not times 2, divided by 2. Okay, we are running out of time, so I need to show you this. Really well done to Gregory. Okay, so I've got, firstly, how many Faradays? I have 3 times 50 times 60, which is, that's not right. So there's the number of coulombs. Now, the number of coulombs, I now work out how many Faradays. That's 9,000 divided by 96,000, which is 0.093 Faradays. Zinc will need 2 Faradays for each 1 mole of zinc. So 0.093 will produce half as much of zinc. Yeah, I hope everybody's got that. Because it's Zn2 plus 2 electrons. Please don't write on my screen. Please do not do that. So 1 mole of this would need 2 moles of this. That's 2 Faradays. So if I have 0.093, then because it is 2 to 1, I will get 0.093 divided by 2. Okay, that's 0.0466. 1 mole is 65, so I get 3.03, which is what Gregory at Mathari Mixed got. Gregory gets the gold medal. People at Dandora very nearly got it right, but they got 6 times. They got 6.06 because they forgot that 2 Faradays makes 1 mole, and therefore they took 0.093 and multiplied it by 65. Okay, there are some more examples, but we're not going to do them today because it is the end.